Okay, before we get started with our experiment today, using our chloroplast that we prepped, I wanted to go back over the actual calculations that I asked you to do. Those calculations you should have already done, and they should be recorded in your lab notebook. I just wanted to double check, make sure we're all on the same page here. So I asked you to calculate the concentration of chlorophyll in our chloroplast suspension, and then I also asked you to calculate how much we needed to dilute that suspension to get it to 0.01 milligrams per milliliter. Quick refresher here. Up top we see Beer's law. Absorbance is equal to the extinction coefficient times the path length of light times the concentration. We already have values. You were given this value in the lab manual for the extinction coefficient, and the path length was 1 centimeter. The last secret ingredient we need to figure out what our concentration is that absorbance that I collected in the last video, 0.63. So if we rearrange Beer's equation to concentration is equal to A over the extinction coefficient times the path length, then all we need to do is plug in our absorbance and divide 0.63 by 34.5, and you get 0.018 milligrams per milliliter. Hopefully everybody got that when they did this calculation. The second part of what I wanted you to do is calculate how much we needed to dilute this. We need a concentration of 0.01 milligrams per milliliter. We have 0.018 milligrams per milliliter. So we need to dilute this somewhat in order to get it to the proper concentration of chlorophyll. The first step in doing that is calculating the total number of milligrams that we currently have in our chloroplast suspension. That's very easily done. We have 2 milliliters. If you recall, we resuspended our chloroplast pellet in 2 milliliters of suspension buffer. So now we know the total volume we have and the concentration of that volume. Multiply the two together and you get 0.036 milligrams. So we know how many milligrams we have. Now we need to know what volume to put those milligrams in to get it to the right concentration. So you can set this up as a simple ratio comparison. We want to know how many milliliters it will take to get 0.036 milligrams to equal 0.01 milligrams per 1 milliliter. So once you have this set up, you can just cross multiply and then divide both sides by 0.01 milligram, and you will get 3.6 milliliters total volume. So you want to wind up with a total volume of 3.6 milliliters, because 0.036 milligrams in that volume is the same as saying 0.01 milligram per 1 milliliter. So that's the total volume we need, but we already have 2 milliliters, right? So we subtract out those 2 milliliters and we know that we have to add 1.6 milliliters of suspension buffer to our chloroplast suspension to get it to the proper concentration of chlorophyll. Again, this should all be in your lab notebook already. If you had difficulty with some of the math and this isn't making sense to you, please contact me. We can work through it together. You never know when you might need to know how to do this, say on an exam, say roughly around midterm. Okay, so we are ready to go with our chloroplast experiment. Let me show you what I have set up here so far. I have one cuvette wrapped in tin foil. That's going to be our dark control. And then I have 5 other cuvettes. To show you these cuvettes, are cubic, so they're not the low volume cuvettes that we used in our chlorophyll assay. You'll notice that two sides are ribbed. Those are the sides that you can touch, and then 2 sides are clear, and that's for the light path. So we make sure that we don't get fingerprints or other kinds of crud on the sides where the light is going to shine through. I have a total of 6 cuvettes set up here. Like I said, that one wrapped in foil is going to be our dark control, and we'll talk about that in a minute. I have one for our blank that we're going to use to zero out the spectrophotometer, and that's going to contain everything that goes in the experimental cuvettes except for the DPIP. So when we put that blank into the spectrophotometer and we measure how much light is absorbed at 652 nanometers by everything but the DPIP, so that when we put our experimental cuvettes into the spectrophotometer, it will only be measuring the absorbance of the DPIP. Very much like tearing a weigh boat. You turn on the scale, you put your weigh boat on it, and you hit tear. That's going to zero out, take into account the weight of the weigh boat, so that you're only weighing what you actually want to weigh. So by using everything but the DPIP, the spectrophotometer will take into account the absorbance of all those other things, the chloroplasts and the buffers. The absorbance of that stuff will be taken into account. So when we go to measure the experimental, you're only going to be measuring the absorbance of the DPIP. So that's our blank. This is one control, our dark control. So what's the function of the dark control? We know by the very name of this is the light-dependent reactions, or the Hill reactions. We know light is necessary. So why do we need to prove that light is necessary by having a dark control? Well, that's technically not really the function of this dark control. What the dark control is going to tell us is there anything else in our system, in our buffers, that causes DPIP to spontaneously become reduced? And if so, that's going to be a problem. So this isn't a check to make sure that light is necessary. We already know light is necessary. This is a check to make sure that nothing in our buffers is reducing DPIP. Okay? The other control we're going to have is going to have no chloroplasts. Again, we know that photosynthesis can't occur without chloroplasts, so what's the purpose of that? Well, that's going to sit out in the light without chloroplasts, and that's kind of a check to make sure that light alone is not sufficient to interact with our buffers to reduce DPIP. Okay? So those are the functions of our two controls. And then I have three other cuvettes that are going to be used for the experiment. My experiment today is going to measure the effect of light intensity on the rate of the Hill reaction. And I'm going to do that by placing these cuvettes at three different distances from the light source, because as you get farther from the light source, the intensity of light decreases by a factor of distance cubed. So I'll show you that setup in a minute. Right now we need to get our cuvettes all set up. So I'm going to put everything into these cuvettes, into each cuvette that's needed except for the chloroplasts. The chloroplasts are the very last thing to go in. When we get ready to actually run the experiment, you'll see I'll put chloroplasts in, give it a mix, and immediately measure it for time 0 and set it in its place. So the chloroplasts are the last thing to go, but everything else can go in now to get prepared for that. So the first thing I'm going to put in is the Heppies buffered saline, or HBS for short, and I need 2.5 milliliters of that in each cuvette. So my Heppies buffered saline, I have a regular 5 milliliter pipette here. So what I'm going to do is draw up 5 milliliters in this pipette and then put 2.5 into each cuvette. One, two, 2.5, and 2.5 for that cuvette. One, 2.5, and 2.5 for that cuvette. And 2.5. All right. Next up, I'm going to add water. My blank is going to get a full milliliter of water, but every other cuvette gets half a milliliter of water. So I've set my pipetter to 0.5 mils, or 500 microliters, and in my control I'm going to give it 2 half mils to take it up to 1 milliliter. That replaces the volume of the DPIP that I'm not going to add to my control. So that one gets 2. Every other one gets just 1/2 mil. And notice I'm not changing my pipette tip in between, and the reason for that is that I'm not touching any solution other than the distilled water with the pipette tip. So I don't have to change it if I don't touch anything else but distilled water. If I were to goof and accidentally touch a buffer, I would have to change pipette tips. There's the water. New pipette tip. And I'm going to add the DPIP. This is DPIP. This is in its oxidized state, and you'll notice that it's very, very dark purpley blue, to me anyway. That's the way we want it to start off with. When it gets reduced, it should turn colorless, hopefully. So I'm going to add 1/2 mil to all but the blank. Blank doesn't get any of this. Again, I'm not touching anything with the pipette tip except for the DPIP, so I'm not changing tips in between. All right. So now everything has been added that we need except for the chloroplast. So other than that, everything is set to go. So I'm going to get the rest of the experiment set up, and then I'll show you the setup. Once the experiment's underway, it's going to be very dark, and I'm not sure how much you're actually going to be able to see besides me actually using the spectrophotometer. But we'll cross that bridge when we get to it. So give me a minute to get everything else set up, and I'll be back. Okay, so to show you the setup, here I have my light source and my heat shield. This beaker of distilled water is going to shield my cuvettes from the heat from the light source so that we're just measuring the effect of light and not the effect of heat. And then as I move down the bench here, you'll see I've marked off 30 centimeters, 60 centimeters, and 90 centimeters. So I'm going to test the effect of light intensity on the Hill reaction by varying the distance of my experimental cuvettes from the light source. So here at 30, I'm going to have my dark control, my light control, or no chloroplast control, and my first experimental cuvette. I'm going to have those set out right here at 30 centimeters. I chose to have my controls at 30 centimeters because if any photosynthesis is going to occur, if any light reaction is going to occur, it's most likely to happen at 30 centimeters. Probably, I would expect least likely to occur at 90. So I want my controls to be right up front. And then I'll have one experimental cuvette here at 60 and my final experimental control here, experimental cuvette at 90 centimeters. Now, I'm going to get this camera set up over here. Show you what I'm going to wind up doing. So here at the end of the bench, I have my spectrophotometer. Again, here's the spectrophotometer part, and here's the computer part. I haven't yet set that up. Get that turned on right now. So here are my cuvettes, and my dark control. When I get started, what I'm going to do is take my first half a milliliter of Chloroplast from my Chloroplast suspension that's been properly diluted, and put it in, say, the blank. And then I'm going to zero out the spectrophotometer. Then I'll be done with my blank. Then when I get that all done, I'll take half a milliliter of Chloroplast suspension, put it in the cuvette, give it a quick invert to mix it up, and then measure it in the spectrophotometer. For the dark control, every time I measure it, I'm going to have to pull this out of its, pull it out of its aluminum sleeve and put it back in. So that's going to take a little bit of doing. For the others, I'll just add chloroplasts, invert, measure times 0, set it out at its place. Again, when I get this started, it's going to be done in the dark. So I'm not sure how much of that you're going to be able to see on the video. Right now I'm just setting up the wavelength. 652. Okay. So at this point, I'm going to want to turn off the lights, and I'll talk you through what I'm doing. You might be able to see some of it here, but again, because it's going to be dark, I don't know how much you're going to be able to see. Alright, I just added half a milliliter of chloroplasts to my blank. Now I'm going to zero out the spectrophotometer. Give it a minute to warm up. Should be calibrating now. Calibration complete. Okay. And you should be able to, I don't know if you'll be able to see this. There. You can see that it's set for, well, it says 651.9. That's close enough to 652 nanometers. And there's the zeroed out spectrophotometer. It's not exactly 0, but it's close enough. So now I am done with this cuvette. I don't need to zero it again during this experiment. Okay. The next step, I'm going to add my chloroplast to my dark control. And then immediately take a reading, times 0, and then set it out in place. That's what my dark control looks like. I need to slip it back into its aluminum sleeve. Close the little lid that I had for it. And we're underway. Now I'm going to put my no chloroplast out in place. Oh. Got to take a reading of my no chloroplast before I put it out there. Keeping an eye on my time, I'm going to take now my 3 experimentals. Add chloroplast to my 30 centimeter. Take a reading. And set it in place. Add chloroplast to my 60 centimeter. Take a reading. Set it out in place. And finally, my 90 centimeter. Take a reading for time 0. And set it out in place. So now every time I take a reading, I'm going to go in the same order. Start with my dark control, then my no chloroplast, then my 30 centimeters, 60 centimeter, and 90 centimeter. And by doing that all in the same order, they should all be about 5 minutes apart. And I've got about 1 more minute before I take my next reading. Reading every 5 minutes. So I'm doing light intensity. You all could have done something like testing the effect of different colors on the cuvettes. The procedure would be exactly the same. In other words, you would put the same things in each of your cuvettes. You'd even use the same controls. And there's my time. You'd use the same controls. The difference would be, instead of setting them at different distances, you would simply wrap each cuvette in a different color cellophane, plastic. Taking my no chloroplast control reading. Here's my 30 centimeters. $60 centimeters. And my 90 centimeters. I don't know why that last one was so jumpy. All right. So as I was saying, if your hypothesis was about the effect of color on the Hill reaction, then you would have added the same things to all the cuvettes. You would have still had a dark control. You still would have had a no chloroplast control. But instead of setting them at different distances, you'd wrap them in different colored cellophane, say red, green, and blue, for example, and set them all equidistant from your light source. And while I wait for the next time point, maybe I can show you what this kind of looks like. Yeah, it's a little bright enough. So you can see a little bit. There's the dark control, the no chloroplast, and the 30 centimeter. There's the 60 centimeter. There's the 90 centimeter. Okay, so now that you see how this is all working, I'm going to go ahead and stop the recording and go through this the rest of the way on my own, collect the data, and I will make that data available to you. If you chose to do colors, let me know, and I have a data set that I can give you to analyze for your lab report based on colors. So just let me know what you want to do, and I will have a data set available for you.